There we go. And let me pass it over to group 2.
All right, I'll get the presentation up right now. All right, and let's share screen. Take it away, Jack.
Everyone see the screen?
We do.
Perfect. All right, hello everyone. I'm Jack Spillman. Thank you guys so much for coming to our presentation today. We're Senior Design Group number 2, also known as Electric Sunflower Technologies. Presenting with me today is Caden Bauer, Adriana DeBoer, Mark Itkin, Bridget Ortiz, Joshua Owens, and Kate Todd. We really hope you enjoy our presentation and ask that you hold all of your questions until the end for the sake of time. If anything's unclear during the presentation, feel free to mark down the slide number, and then we can go back at the end and address any questions you have. I wanted to start by telling you a little bit about our team and our motivations throughout this design process. And the 3 pillars of our motivation come from business author Jim Collins's Good to Great book, when he calls it the Hedgehog Concept. So our first motivation is, what are we best at? And from meeting the team the first week of class, it was pretty clear that we have a ton of experience in different design groups. Myself, I'm in Vex Robotics, but we have people from Gator Loop, Solar Gators, Gator Motorsports, and I was really impressed at the amount of technical knowledge that we all had. And so experience in these groups tells me that, from the creative ideation process to fully operational process, we have learned, what works, what doesn't, and how to work as a team. And a lot of times people without this type of experience will come in with their crazy designs, but they don't always work. And we know that feasible designs are the best, and we know how to create these type of designs that not only work, but are going to excel at what we have to make them do. And so now our second motivation, what are we passionate about? And that one was very obvious, and it was sleep. And as busy senior students, we have a lot on our plates right now. And so we asked ourselves, what kind of design can we make that satisfies our need for sleep? And the way we did that is to keep the design simple in terms of the mechanisms, the number of parts, and using ideas that we understand very well, not stretching ourselves too thin. This made the design process a lot easier. It made our product very simple to understand, and it prevented any overnighters in the library. I don't think we were at the library past 12 throughout the whole year, which is very impressive. And finally, what drives our economic engine? And we're about to graduate. We need to find a job, and we're all working on trying to sell ourselves, sell our value. It's always on our mind. So in terms of this design process, we thought, all right, we want to get hired by this customer, and we want to be able to build our prototype because we think it's a great design. So how are we going to get picked by the customer? We should address every single customer metric and communicate with our professors and the customer as well as possible. So this resulted in a really fluid design that is constantly changing, and it'll probably change a little bit by the end of this week when we submit our final design report. At the end of this whole thing, we believe we have a really robust design, and I'll give it to Mark to give a higher level breakdown of our sunflower heliostat.
Thank you, Jack. So to give a general overview, our system is comprised of 4 individually controlled heliostats, with 2 heliostats on the lower step and 2 heliostats on our higher step. These steps are made of concrete and are separated as part of our step and stagger system to reduce shading. For our reflective surface, each of the heliostats has 4 small mirrors mounted that make up a total of 1/4 meter squared area per heliostat. Together, the 4 heliostats are able to produce about 250 watts of energy. From there, the reflective surface is then adhered to the reflective backing, which is made up of 2x4 pressure-treated wood beams. An epoxy adhesive is used to keep the mirrors secured to the backing. And then in order to actually move the surface and backing, we have our motion system, which is composed of 2 high-torque gear trains that each control an axis of rotation. These gear trains are then able to continue operating all the way up to 40 miles per hour winds. The motors are then controlled via a Raspberry Pi board, and there's one board located between the 2 heliostats on the top step and the one board located between the 2 heliostats on the bottom step. The Raspberry Pi communicates back and forth with the motors in order to adjust the position of the heliostats accordingly. In addition, all the electronics are contained in sealed enclosures to protect from weather and other environmental elements. Now, I've given a small overview of our system, and we'll now break down each of our subsystems. Bridget, we'll start you off by describing the reflective surface subsystem.
For our reflective surface, we were between various shapes and decided to go with a square. It is simple and aligns with our motivations. It is easier to manufacture, and the other systems will integrate well with it as well. As for material, instead of going with a multi-layer surface and having to add a different complexity, we decided to go with annealed glass. This allows for minimizing optical losses from any sorts of bending. And finally, we chose 4 mirrors for 1 heliostat. The reason for this is it decreases the wind forces that will be seen, but also if for some reason 1 mirror breaks, it is easier to replace one and you can use less mirrors, less material when being replaced. There's the smaller area of glass per mirror allows for better loss dispersion. And I will now hand it off to Caden, who will talk a little bit more about the thermal calculations.
All right, thank you, Bridget. So each one of our modules is able to reflect 253.78 watts of power. This would require about 3,941 of our modules to be used in order to complete the customer's need of 1 megawatt of thermal power produced by our solar field. Obviously, these numbers are highly dependent on the module's position in a solar field, as well as the time of day and year. Most of the sun's power can be captured by a receiver from heliostats that are closer in proximity due to less optical losses and small angles of incidence. Modules that are located further away will be more likely to experience some power loss due to factors such as loss dispersion. For the purpose of our calculations, a module placed 50 meters north of a 100-meter tall tower was used in order to obtain the general estimation of the solar field that I just described. The calculation itself involves multiplying the total solar radiation leaving the module, the reflective area of the module, and the optical efficiency of the system. The optical efficiency was estimated to be a function of the mirror's reflective efficiency, for which silverized annealed glass is about 95%. The solar radiation leaving the heliostat is a function of the solar radiation striking the Earth's surface and the angle of incidence that was previously mentioned. More in-depth calculations of these variables can be shown at the end of the presentation if requested. Another requested feature of a design is a solar concentration ratio greater than 1,000 suns. And if we use our estimated 3,941 modules and a receiving aperture area of about 1 meter squared, our system will be able to provide a solar concentration ratio of 1,062 suns. This value is determined by the solar concentration hitting the Earth's surface, the geometric concentration ratio, and the optical efficiency as previously discussed. In order for a reflective surface to be effective, though, it needs to have a rigid backing that will support the weight of the mirrors.
For our reflective backing, we decided to use 2x4 pressure treated cedar wood that is then kiln dried. Wood is cheaper and yet is very strong enough for the intended application. The fact that it will be used in Las Vegas and that the wood is pressure treated, there is no concern of the decay, and it should be expected to last to 20 years, requested by the customers. And because of the drying process as well, there's going to be no foreseen shrinkage or the shrinkage as well that you would see from wood. And then as well, any optical losses that could be seen from the support of the backing is minimized because there's not as much as deflection from this wood. And the lightness of the wood also that is going to be actuated from the motors is also minimized here.
So one of the main obstacles that we faced as a team was the difference in thermal expansion coefficients between our reflective backing and our reflective surface. So wood has a much larger coefficient than glass and would therefore want to deform many times more than the reflective surface. This causes a lot of large internal stresses in both subsystems. We're able to overcome this challenge by using 6.31 millimeter thick application of epoxy adhesive, but we would like to point out that this is an over approximation and it needs further experimental testing in order to come up with the final thickness, but we expect it to be significantly lower. This pliable adhesive is thick enough to prevent the differences in deformation from becoming an issue while still maintaining a solid contact that can last the requested 20 years. So another large concern of ours that I'm sure a lot of you guys are thinking about is wood's ability to shrink and swell with the changing humidity rates. This deformation could possibly cause internal stresses and optical losses. We've determined that this deformation is less than 0.2 millimeters and not detrimental to our system's functionality. This is due to the fact that Las Vegas only really sees a relative humidity around 20 and 40%, and this would only marginally change the moisture content of our wood and keeps our deformation at a minimum. We use the appropriate shrinkage coefficients of cedar in order to carry out all of our calculations and make sure we had accurate results. We also added slots between all of our wood joints at all the bolt points, and we did this in order to reduce the stresses in between the wood connections. These slots will allow for small movements which prevent any sort of cracking or splitting of our backing, and is commonly seen in furniture making as well. Now I'd like to introduce Adriana, who will talk to you a little bit more about the bones of our design.
Thanks, Kaden. The structure subsystem consists of 2 steps, an upper step and a lower step. The dimensions of the upper step are 2 meters by a quarter meter by 0.4 meters tall, and the dimensions of the lower step are 2 meters by a quarter meter by 0.12 meters tall. And these steps are located about half a meter apart. They are staggered so that the heliostats are not directly in line with each other. Particularly, the heliostat on the left of the bottom level is located between the 2 heliostats on the upper level. The distance between the 2 heliostats on one step is 0.5 meters for this purpose. Therefore, the total square footage of each module is 2.04 meters squared. The nature of this design is to eliminate shading between heliostats on the same step as well as between the 2 levels. The structure is made of concrete as it is inexpensive and able to sustain the weight of motion and reflective backing surfaces systems without tipping or deflection in the motion system. Now let's take a look at the shading removal by the structure subsystem. In order to make sure that there was absolutely no shading at any point of the year, there were 2 extreme scenarios that we had to consider. The first, which set the front to back spacing of our platforms, was the solar elevation angle on the winter solstice, which is at its lowest here. In the diagram on the left, you can see how we visualize the solar rays to set the gap between modules. The step design allows much closer spacing between the modules than if they were on the same elevation. The second extreme scenario, which we use to calculate the left to right spacing on each step, is actually in the morning on the summer solstice. On this day, the sun's trajectory is most directly overhead and shades heliostats from east to west. We decided to start collecting power at 8:15 a.m., which translates to a solar elevation of about 32 degrees. We chose 8:15 because there's about 9 hours of peak sunlight on the summer solstice, and this collection time splits that between sunrise and sunset. Next up is friction reduction on the structure subsystem by Kate.
Thank you, Adriana. The structure model comes with a furniture slider and a bushing that helps support the heliostats. The furniture slider made out of nylon is placed on the bottom surface of the structure, and its friction coefficient is 0.2. The bronze bushing is placed on the top surface of the structure, and the friction coefficient for the lubricated bronze on steel is 0.16. Both of these features reduce the friction in the normal operation of the heliostat. And to talk about the motion of the heliostat, here's Joshua.
All right, thank you, Kate. So as mentioned earlier, our motion system allows us to track the sun in 2 axes. And to control the azimuth position, which, if you're not aware, is the compass direction from which our sunlight originates, we're using a worm gear drive system at the base, which you can see in our image. And that has a maximum range of motion of about 330 degrees. And then to control the elevation angle, which is just the position of the sun above the horizon, we're using a custom gear bracket system that you can see at the top there. And that has a max range of motion of 65 degrees. We'll talk a little bit more about that later. We chose to use gear trains for the system to increase mechanical advantage here, because that would allow us to use smaller motors with less torque and decrease the cost, since those electronic components were a major factor in our cost calculations. Now first, we'll talk about the worm gear system at the base. To select an adequate motor for this application, we had to consider the torque that it would need to overcome from forces of friction. That is the contributions from our brass bushing and our plastic slider. And it also would have to overcome torque in the worst case from wind that occurs on this side profile of our reflective surface and reflective backing. The max required torque that we are predicting would be about 8 pound-inches. And thanks to our 30-to-1 gear reduction that we're seeing down there, we have up to 75 pound-inches of torque available to use. So our motor should not be a limiting factor here. Now, to keep contaminants out of the gears and electronic parts that we have down there, we've designed a simple plastic casing with snap fits that can easily be removed for maintenance, and that shuts out all of the elements for prolonged life. Now, to talk about elevation angle tracking, we're gonna take it back to our original design here. In this iteration, we used a servo and pushrod system to move the backing, and we decided to use U-bolts to form the hinge here. So right away, there are some issues with this design, but our primary focus is going to be the torque rating of our servo. So at max tilt, the center of mass of our reflective surface and backing is going to generate a moment about our axis of rotation. And we're also going to consider the lift force from wind at our worst case. That's going to contribute to torque around this axis as well. So to determine this lifting torque from wind, we've approximated our surface and backing here as a flat plate in laminar flow, and we've used that approximation to determine our center of pressure. So with all of those calculations, we determined a total expected torque requirement of over 90 pound-inches. And that was just simply too great for our weak little servo to control. And in addition to that, there was also a lot of complicated geometry and optimization that would have to be done with this design. And so in keeping with our motivations of simplicity, we just completely scrapped this concept and switched over to the gear train idea that I presented just a couple slides ago. So I'll turn the presentation back over to Jack, and he'll discuss more of that gear system.
Great point, Dr. Trump. Yeah, so going back to our high torque gear assembly, this was our solution to our servo problem. Our servo it didn't have the range of motion, and it definitely didn't have the power to withstand the wind and the weight of our reflective backing. So as you can see here, it's a pretty high gear reduction. It's an 8-to-1. And with this, our small DC motor is able to withstand forces up to 48 miles an hour. We have a very high mechanical advantage, which was kind of our main goal with this motion subsystem, which is going to keep our costs significantly lower. And with this smaller motor, we reduced our motor costs by 62% from our initial design. As you can see, looking at the picture, it's much simpler. It's going to save us costs in manufacturing, material, maintenance, which also aligns with our Hedgehog concept. It's got a great range of motion, so we didn't have to worry about any of those limitations from the servo design. So looking into these gear brackets a little bit more, we can go to the next slide for me. Perfect. We had a couple unexpected benefits when we were implementing this new design. We were able to make this very simple. As you can see, there's very few screws or fasteners needed for this entire motion assembly. The only ones that are needed are to attach the gear brackets to the reflective backing. We decided to use nylon bushings in a D-shaped flat to give us the range of motion needed, and also to secure to lock the motion of the gear with the reflective backing. And with these gear brackets being injection molded plastic, lubrication was not as important as if you had metal on metal contact. And because these are moving at such a slow rate, we decided that an enclosure was not as necessary, because the wear on them would be so small that throughout the day, you're hardly going to see these things moving unless you have a time-lapse video of them. And another added bonus is that you can see that these gear brackets are actually identical, but we're only transmitting torque to one of them. So to increase the life of our parts, during the maintenance procedure, we can actually just swap them if we see that there is any wear going on. So that's going to double the effective life of our part. I guess now we can go a little bit into the high wind safety mode that we have determined is necessary. Our motion system is able to withstand winds of up to 48 miles an hour. So the limiting factor is not our electronics. It's actually just the weight of our heliostat and the nature of the flat plate estimations that we made. First, we had to do is we had to estimate the weight of our smaller modules in the front. They have a smaller support pole, so they have a lighter weight. So we went back through the lift calculations for worst case scenario, and we found that at 40 miles an hour, the lift vector would equal the weight vector going down. This is, of course, worst case scenario, assuming no friction on its way out. So we decided this was a safe bet for enabling our high wind defense mode. So in this defense mode, all the heliostats go flat, which cancels out any type of lift vector. And in this position, the heliostats can actually withstand winds well over 100 miles an hour. And the maximum wind speed that's ever been recorded in Las Vegas is 92 miles an hour. So if we were dealing with hurricane force winds, there'd also be probably the great flood and locusts and meteor strikes. So we feel confident that our design is structurally sound, and this defense mode is going to be able to keep our heliostat field operating throughout any type of weather condition. And from doing motor torque calculations and looking at the stall torque, we found that in worst case scenario, meaning the heliostats were at the largest tilt, they would be able to go up into their defense mode at, that's a good point, Trom. We didn't do those calculations, but if they were worst case scenario, they'd be able to tilt into flat position in only 7 seconds. So you really don't need an advance warning to enable this and to keep the heliostats safe. So now I guess I'll shoot it back to Mark to talk about how we control this motion system.
All right, thank you, Jack. So continuing off motion, it's important to make sure that we actually have the capability to move our motors, and our electronic system comes into play here. And the main controller for this is the Raspberry Pi Zero W. A small computer with Wi-Fi capability, the Raspberry Pi is able to communicate with the motor encoders from 2 heliostats, and then it's going to be able to obtain their rotary position and then change that position as necessary. In addition, switches are implemented to provide baselines for motor position, and motor drivers are used to provide necessary voltages to the DC motors. Other than that, the majority of electronic components are within sealed plastic enclosures to protect from the environment. The enclosures make use of snap fits and O-rings, as mentioned earlier, to both allow for easy access while securing the perimeter from weather. In order to provide a better view of the electronics here on this slide, though, the plastic enclosure on the bottom right is hidden so you guys can see the electronic components. Moving on to give a little more detail, outside of the Raspberry Pi, our smaller components in our electronic system also play a vital role in the upkeep of the heliostats. To start, we use Omron long lever switches to set baselines for rotations of each axis. This way, on startup of the system, it can be rotated until the switches are activated, giving an initial position to compare our motor position to. One switch is located within the bottom enclosure and is activated 90 degrees clockwise, which you can see here on the bottom left, while the other switch is located above the upper DC motor and activates a few degrees after the heliostat's horizontal position. So this is where you can see our pin that's going to press down onto the switch. In addition to the switches, we also have IRF 520 MOSFETs, and those are used as our motor drivers for each of the motors used. These transistors allow us to provide the necessary voltage that we need to the 12-volt DC motors without exceeding the power draw from the Raspberry Pi. In addition to the MOSFETs, fuses are also installed between the drivers and the motors to prevent overcurrent caused by the motors being over-torqued in the case of that happening. In particular, a 2-amp fuse is placed between the top DC motor and its driver, and a 1-amp fuse is used for the bottom DC motor accordingly to their current draw. To give a little more detail on the actual power diagram, here we have the power diagram for each motor. And so the way it works is that our 12-volt DC power source feeds into the module, and this power is then provided is then fed into each one of the MOSFETs. And there's one MOSFET for each motor. The Raspberry Pi then controls whether or not the power is being fed to the motors or not by sending a digital signal to the motor drivers. From the MOSFET, the power out is then connected to the respective motors with a fuse placed in between in the case of continued high current draw. The same setup is also implemented for the second set of heliostats, as this is for just 2 heliostats, so 1 Raspberry Pi system. Now, moving on from our subsystems and their components, we also want to share some additional details about our full system. And we'll start with the cleaning and maintenance procedure for the sunflower heliostat.
Due to the fact that the heliostats are exposed to the air, dust and dirt accumulate gradually on the surface of the reflector. As a result, the reflective property of the mirror gradually decreases, thereby reducing its efficiency. To maximize the efficiency of the heliostats, several cleaning methods can be applied. Using a self-powered machine to have an automated cleaning system on the heliostats that cleans itself regularly may be effective, but it may increase the cost of manufacturing the heliostats. Instead of expensive cleaning machines, manual maintenance can be done regularly. Compressed air can be used to remove the dust or sand on the reflective surface of the heliostats, and it can be used for every 2 weeks, but can be repeated as often as needed. Another method to clean the reflective surface would be using high pressure water with the detergent if necessary. The detergent should not have any strong chemical or mechanical bonding to prevent the damage to reflective surfaces. Cleaning with water pressure can also be done as frequent as necessary, but for the wood sealer needs to be applied every 2 years for the longevity of wood. Now let's take a look at the overall cost.
All right, now for the most important part, the cost. With our current design, we're looking at a total assembled cost of about $374 per square meter of reflective surface, with the manufacturing and assembly costs being determined by general process estimates and standards from Boothroyd and Dewhurst, and the cost of off-the-shelf parts and raw materials just being determined by our best estimates of bulk order costs. But actual quotes from suppliers weren't obtained at this point, so we expect those numbers to change slightly. One of our limitations we ran into when pricing all of this out was just the need to have multiple heliostats in our module. The motors and electronic components were one of the most expensive components, and that cost really added up with our total of 4 heliostats. And also some of the other prices and of components were slightly inflated at this time just due to economic factors we can't really control. So overall, costs can fluctuate a little bit. We understand this is pretty far off of our customers' demands, but I'll let Jack continue and explain why we think that's okay.
Jack, you're muted, unfortunately.
It was bound to happen once. All right, so yeah, we understand that the cost is a little bit higher than the customer metric, but our main motivation was to deliver a product that does exactly what the customer asks. We did not cut out on any electronics, on any system capabilities, and we used the correct equations. We didn't do any fake calculations to save on weight or structural cost. We think we have a really simple design. It's easy to understand, it's easy to build, which will be great for EML4502. And we know it'll work because we've implemented reliable technology and mechanisms that we know have worked through our experience in our various design groups. We've done a ton of time debating every single customer need, and we've worked hard to make sure that we're addressing all of these. We've talked about these customer needs so much that Dr. Traum has actually given Mark his personal phone number. And by this point, he's probably blocked him from all the questions that he's gotten. But I am very appreciative of our team. And I think every person contributed greatly. They made their own sacrifices and they applied their skills well. It really changed, how it really changed what I think about group projects. And I'm really proud of the team. And we're really proud of this design. And we hope that showed in our presentation today. And that wraps it up. Thank you again so much to Dr. Traum, Dr. Nemi, Dr. Sheffy, Dr. Trainum, Dr. Greenslet, and all the sponsors today, Rigo, Northrop Grumman, Cummins, and Carrier. And I guess now we can open up the floor for questions, and we'll gladly go back to any slide and clarify to go more in depth if needed. Appreciate it.
I'm not going to have any more professors to talk to if I'm going to keep getting blocked like this.
I've got two quick things, then I will go and allow everybody else in the panel to chime in. First things first, I really like the fact that you actually explained the electrical stuff. I think it takes cojones for a bunch of mechanical engineers to actually dive into the electrical and understand the electrical system. So I want to first say, like, good job going that route and not just having it be like a basic wiring diagram, actually showing kind of how the logic behind the system. That was good to see. My questions are related to your choice of wood. And it just so happens that I woodwork I moonlight as an amateur woodworker when I have time and I'm not, crazy busy. And you directly compared it to aluminum. Rolls eyes. Thanks, Matt. You directly compared it to aluminum. So aluminum is about 7 times stiffer than cedar by modulus, but only about 5 times denser. So, and as we've seen, the aerospace industry gets away with, I mean, there's a wonderful story of the Spruce Goose, which I don't know if you guys are familiar with that airplane. But then beyond that, airplanes are built out of aluminum for a reason. So, why not play around with geometry and aluminum to try and get your stiffness there? If you think about it just roughly moment of inertia, you could get by, you could get by with something that is half the height and still be about the same total stiffness by switching, because it's 7 times stiffer. And, having the height is about a factor of 8 on moment of inertia. So why not play around with geometry? Why go with cedar and not play with geometry to keep the weight down or to keep costs down for total volume?
Aiden, you want to take this one?
Yeah, so we did look at aluminum originally. We looked at aluminum, we looked at steel, we looked at cedar. And we actually had a lot of discussions about which one we should choose. Part of the reason we ended up going with wood was partially the thermal expansion rates. Aluminum had a little bit also with the thermal expansion coefficients, and we were just debating back and forth on the best ways to go. I believe we just picked cedar after going through the Ashby plots as well, and that and aluminum were pretty close, and we just kind of decided we thought it'd be cheaper to go with cedar as opposed to aluminum.
Yep. And on top of that, in terms of actual costs and like obtaining it, aluminum, if we did decrease that height in half, I think a simple shape to go with for aluminum would have been like a hollow box in terms of something that's off the shelf and not really something we have to manufacture on our own. Even that shape with a smaller size was more expensive than getting off the shelf wood and cutting it down to 4 pieces, because each one of these heliostats, the backing is entirely made of just one 2x4 8-foot long wooden beam. So while the stiffness of aluminum, and even if we were considering steel, was much better than what we're looking at for wood, the cost and ease of manufacturing was definitely driving factors for why we kept going with wood instead of switching back to metal.
What about like L-shaped or C-channel?
With if we were to place all of our 4 kind of bars with C channels and with L shapes, there would be additional concern about possible torsion due to the open-celled shape of the components. In terms of actual cost for those components, I wouldn't be able to give you an exact comparison at the moment, but it would definitely be cheaper than doing a hollow rectangle. I'm not sure if it would be still cheaper than our wood, which is $6 for one entire heliostat.
One heliostat being like the set of 4 or one of the individual?
One of the individual ones.
Okay.
You are probably correct on a cost basis.
Yeah. I'll throw out, it does introduce a number of other things, and I wrote down a lot of them, and then, through the course of your presentation, I think you addressed most of them. The fact that it's dried, so, you're counting on it not warping. I would suggest that depending on how far away you are from a collector, even a small amount of warping could be fairly significant in terms of your aiming precision. But you did touch on that. In terms of growth, with moisture uptake, with thermal changes, you're saying you're slotting the holes to allow that expansion to happen freely. So that's at least showing that you've thought about that. Although I would suggest that grain on grain wood, as it's expanding and contracting, it's not going to be frictionless. So that might still be something that you'd want to take a look at. I have a question about the just general setup there, right? So you've got these two fairly big steps, and you say, well, we put the one higher behind it to get them out of the shade, right? So what do you do for the next row? Because these all live in an array, right? So the next row would be that lower step, unless you continue building these up like a stadium, right? So how densely packed can you get these and not have those shading concerns?
Jack, you want to go for this one?
I can take that. You can actually go back to what is it, slide number 11. So one of the main customer metrics was to decrease the ratio between reflective surface and then module area. And by doing the step design, we can actually make the front to back spacing between these heliostats a lot closer. We did consider the field layout. Of course, that wasn't explicitly asked for us to think about, but that's also why we did our stagger design. And so the front of the next heliostat would be shifted slightly over, so it wouldn't be shaded by that top one. But basically, to find the spacing between one module to the next, you could flip this image on the bottom left to have the sun coming from the opposite direction, and then you would find the height of the next bottom row of the heliostats. But with the step, we're able to lower the overall area of the singular module, which is what we were asked to do.
I wonder if that's maybe the customer not quite understanding what their need is, or maybe a miscommunication between the two teams. But yeah, I mean, I would expect with kind of the stagger that you have, that you wouldn't need any step necessarily, and not get significant shading. But with the step that you do have, any shading that you have, you're going to need that much more like lateral spacing between modules that could impact the overall amount of land that you need to effectively meet your 1,000 suns criteria.
Yeah. So one of the customer asked us to eliminate all shading, and so this spacing was derived from worst case scenarios: the front to back spacing from the winter solstice, and then the left to right spacing from the summer solstice. So if you were going to allow a little bit of shading, you could definitely make these a lot closer, but that's why we decided to go with the step design, so that in this worst case scenario, we're still not getting shading. And if that step weren't there, there'd be times in the day where the front surface would shade the back if the angles lined up properly.
Yeah, and particularly in terms of on the same level, we're talking about the one of these heliostats rotating about its central pole. If they're on the same level, you might see shading diagonally onto another heliostat, even with the stagger. And so that's another thing that the step seeks to reduce, any type of possible shading going diagonally, especially for the heliostats that might be on the edge of the field.
Can you guys roll back to slide 9 real quick?
Sure.
No, that would work. Never mind. I was going to comment on the slot direction.
Mhm.
Because the piece that's in the foreground, the wood would actually expand in the other direction. but it's the piece behind it's the one doing the expanding. I'm still not certain that that's the right way to, the right orientation for those slots, but that's just me being pedantic.
You guys, I have a question about your previous slide.
Slide 8.
No, I'm sorry, the one we were just on.
Going all the way back
Slide
to
11.
24.
Yeah, I think it's, there we go. Can you clarify, and perhaps I missed it, each one of the, so you have 4 heliostats here.
Mhm.
Each one of the ones that we picture, is that a total of 1 meter squared, or is the total across this whole combined all 4 1 meter squared?
All combined 1 meter squared.
Okay, so one of your customer needs, I believe it was number 10, at least on the copy that I got, it was saying that you want to reduce the module area relative to the reflecting area. And then it gave a specific example of don't have 1 meter squared of reflecting surface on a module with an area 10 times larger. And it's kind of looking like that's exactly what you did here. So I'm curious why that choice was made.
So I'll take this one. So so in total, our area that this takes up is 2 meters squared. And the thing is that some other teams, they have designs that usually kind of focus on one heliostat essentially. And so the question of shading to other heliostats in the area doesn't get included in their module area. So if we were to take out some of the spacing we've created in order to consider for shading in a full field, our area is much lower. But due to our fact that we're trying to incorporate our shading consideration as part of our total module, our area is a little bit larger. But it's still it's a 2-to-1 ratio compared to the 10-to-1 ratio that's given as example in the customer needs.
Okay, I guess I'm just picturing it as like, if given a certain azimuth, and I think you were speaking about this a few minutes ago, given a certain azimuth, your next module would have to sit far back from this module. And so the relative total area that you would need to kind of make this work would be pretty large. But anyways, I have one other question. It's related to the cost. Can you go back to the cost slide?
Sure.
So if each one of those is only 1/4 of a meter squared, then in reality, each unit would need each module would need to get to the 1 meter squared reflective surface, you would need 8 encoders and 8 motors. Is that correct? If each one of those units is only 1/4 meter squared, right? Okay, so I work with encoders and purchase encoders regularly, and even a cheap one is about $20. So if you need 8 of them, you're talking about $160 just in encoders. And we also need 8 motors. We need, so I guess, where did this pricing for OTS parts come from?
So in regard to the encoders, this might also just be on our part with our limited experience with electronics, but all of our DC motors that we're using, they have encoders on the ends of them for getting their motor position. So
Okay.
we were using those as our way to know our motor's angle at any point.
Okay, so then what's the cost of the motor that you're using for this cost estimate?
Josh?
The total cost of our motors, it comes out to roughly $70. I guess this wasn't
For 8 motors?
Yes, well, let me pull up my cost details real quick. But I guess this wasn't made clear in the presentation, but these are very small motors that we've selected because of the gear reduction that we can get. So the motors that we're using were small and included a simple magnetic encoder on the back. So that cost was all wrapped in together. Let's see, our total cost expected for motors is around $75.
Yep.
For all 8.
Okay, that seems low to me. I'm not going to question too much further on it, but anyways, so that was my main concern was really, this cost looks like it's more likely for one of those panels rather than all 4 together. So that was that was my concern there. I do want to say that I do appreciate you talking about encoders and the stop switches and whatnot. Just a thought moving forward that when you're putting these things into the system, just recognize that you don't just want the stop switches to be there to set the beginning angle, but also, you know, what if you lost control at some point when the motors are moving? You need something that's kind of an emergency stop as well. So.
Okay. Okay, we'll definitely make sure to take that into account.
Yep. Thanks. Good job.
Thank you.
And jumping at that, she brought up kind of what I was concerned with the coder. So I think, you know, fantastic job if you were able to price motors for that includes an encoder. I did want to mention with one of the limit switches for the azimuth, your travel of the peg on that shaft is in a horizontal direction and the receiving switch is vertical. Just, you know, turn it around. Make the switch horizontal too.
Are you talking about
Maybe.
oh, I
Yeah.
just didn't pull off.
So that's not really quite the appropriate type of
There we
switch
go.
for that. You might have something with a roller on it. Actually, I guess that might work.
The
Just seems
idea is
kinda
that
off.
it's a long, in terms of, are you talking about
Because you
this-
don't want it rolling. You don't want it going backwards the wrong way and flipping it upwards. That's the kind of switch that you specified. So never mind. That might be your best bet.
Yeah. The intention of these switches is since they're only mainly intended as a stop, so we know what our initial position is that each of the pin and the small piece of metal are both located close to the end to make sure that it's pressing into the plunger with the lever.
And congratulations on using fuses. Yours might be the only one that does not burn down.
That's the hope. Though I'm still not sure about meteor strikes.
Yeah, we're working on those calculations, but
Yeah.
All right. So actually there's a happy accident in the schedule, which I just noticed, which is this group was meant to end at 2:45. And we were supposed to go right on to the next Mech 3 group. But I'd scheduled the next Mech 3 group to start at 3 instead of at 2:45. So we actually have a little 15-minute hiatus that I hadn't anticipated until we actually got into the schedule. So I let the questions go a little bit longer because it was a good discussion, but we should probably wrap up there just to be sure that we're not over inundating this group with too many questions.
We'll take them all.
They're doing pretty good with them though.
Well, if you want to keep going, we've actually got 8 more minutes, but
Yeah, actually, real quick
Okay.
question, actually. Show of hands, how many of you guys are a part of one of the design teams here? So it's like half the group.
yeah, Mark is a president and captain of Gator Loop, and I'm the captain of Vex Robotics as well.
Sweet. Yeah. Good job, guys. Way to go.
yeah, very good. Okay. Well, so then
Any other
let's,
questions?
yeah,
If you want them, I've got more. I know Brad's got some too. We were talking in the chat, so maybe I'll let Brad ask a few of his.
Sure. Maybe I have time for 1 or 2 questions.
Brad, you might be muted.
Thank you. Yeah. I was wondering if like a hard stop would be something you would want to include in the structure as well, in case the switch is slow to respond, would save the switch from getting crushed. I don't know if that's commonplace.
We definitely could possibly include a hard stop. Going back to the switches, just kind of before it gets to its max travel position, or right at its max travel position, I guess we can include a hard stop to help making sure that the switch doesn't get pressed too far.
And then, yeah, you had mentioned swapping the top actuator around. You'd be rotating the actuator, not switching the gear assembly, right? It looks like you included holes there to allow for that.
But we were actually going to dismount the gear brackets and flip them. The motor would stay in the same place.
Yep. That's due to a small inconsistency due to not completely updated image, but our main goal with this is to switch out the gears.
Okay. Could you turn the motor around? Would that be fewer screws? Yeah.
Hmm?
Could you turn the motor around instead? It looks like you have holes there that would allow for that.
We were considering switching around the motor. The main reason we didn't is the fact that in order to do that, we'd have to essentially now have two different gear brackets due to the fact that the parts no longer be identical. They have to be mirrored. And so now you need increased cost to now manufacture two different parts instead of just one.
Your control would be backwards too.
Yeah.
It would be, yeah.
Actually, you could put another pin on the same side, you know, on the other extreme, so that when you molded it, then it would work if you flipped it. So we could also do that.
Yeah, but of course they would also need a change in control.
Yeah.
And then, yeah, I'll ask one more question, then I'll let someone else. For the coefficient of thermal expansion of the wood, it looked like you gave one number. You might have thermal expansion or coefficient of thermal expansion in the grain direction that is different than what it is in the transverse direction. So.
Yep. Kate, and actually, if you want to talk about that real quick.
Yeah, I believe when we did it, I know there are two different thermal expansion rates, one for with the grain and one against the grain. I believe we picked the one that goes with the grain, just to account for that correctly. But I can definitely go ahead and double check that as soon as this is over and make sure that's up to date in our final design report.
One thing for sure, though, we did purposely choose the one that was in the larger, So I think going against the grain, it was like 10 compared to the 30 of the other one.
So this would be a worst case scenario, either direction that it expands.
Okay, yeah, because that might help you if I think with the grain direction will be less than transverse. So it's good to be conservative, but also if you know which way the wood's going to be, that could out a little bit.
Yeah, definitely might help decrease the thickness of the epoxy.
Man, aluminum would be a much better match to that glass. Oh wait, no, I'm thinking degrees Fahrenheit. Now I don't even know if it would be a much better match to the glass. Real quick.
I think it was 23.
Yeah. Oh gee, I don't even know in Celsius. You're using a lot of concrete here as a step, and it doesn't seem like it's doing much for you that a longer post wouldn't do. Did you look at a trade and as to whether you needed a large step versus a longer post?
So let's see. When you guys want to step in, or I can just quickly answer this question.
So we did. Okay. Yeah. Oh yeah. We did do some calculations on the bending moment of the pole itself when induced by wind, and by increasing the step instead of the pole, you kind of decrease the bending moment, like the length of the arm. I think that was one of our main kind of goals. So yeah, to decrease the deflection as well onto the worm gear.
And then in addition to that, the other thing is that we do want to rotate our system about the pole. And if we just had a longer post, we'd still need some type of structure or something to lift the pole off the ground so that it actually would be able to rotate instead of just sticking it into the ground. That we are approaching 3 o'clock, so I think that'll probably be the end of our questions.
Yeah, we do now actually have a hard stop because we need to move to one of the MEC3 pipette groups at 3. So probably, I think Dr. Nemi already left to go do that. Yeah. So anyway, we'll call it quits there. Thanks for an extra 15 minutes of very interesting technical discussion. I'm glad it was you guys that were getting roasted and, not someone else, because, payback for Mark calling me on my cell phone like every 15 minutes all semester. So just kidding. Anyway, want to thank you guys for your presentation, and really good job. I'm glad that you went with the wood, right? That was, I think I told you in the very beginning, if you're going to go with the wood, you have to own it. And I feel like you guys, really analyzed it and owned it in the way that we wanted to see. So appreciate that. With that, we'll stop recording